afternoon, Mustafa sir.
Hello, good afternoon. Can you hear me right?
Yes.
Okay, good.
Okay, we can start.
Yes, I'm ready.
So, very good afternoon, everyone, and hearty welcome to the second class of electrochemistry by Dr. Muhammad Mustafa from ISO Pune. Yesterday, we had a very excellent session, very great introduction to electrochemistry. So, definitely, I'm sure everyone is waiting for the remaining classes, and we are all waiting for that. So, hearty welcome, Dr. Muhammad Mustafa, Head of the Department of Chemistry, Dr. Tanya Francis, Dr. and other teachers, and all the dear students. Welcome again. So remember, we will be continuing this class session tomorrow also at 2:30 p.m. So we'll have a great class on electrochemistry in these 2 days. Okay, and for questions again, we will be sharing that Google form link in the chat box and also in the WhatsApp. And later on, if you have questions later on, you can post there. We will give to Dr. Muhammad Mustafa. And in between, if you have questions, you should feel free to ask. You can talk to Dr. Muhammad Mustafa in between. So welcome once again. Yes, Dr. Mustafa.
Okay, so thank you again, Dr. Jomon, for your introduction and background information about the lecture today. And I think there was a question yesterday which was posted by one of the students about, I think electric eel. Yes, so I was very excited to read the question, in fact, because the question, I think, if I remember correctly, it was about, it's a very nice question because when I read the question, initially I got scared. I thought I should skip today's electrochemistry lecture, in fact. But okay, then the question is, when electric eel is present for example, in a river, why not other species are affected by the presence of electric eel? That was the question, because after all, electric eel is a deadly species. It produces 600 volts. So why not that voltage is affecting the other aquatic species in those ecosystems? That was the question posted by one of the students. A brilliant question, no doubt about that. Yes, so I think the answer, I will give it in an indirect way, because I am only a chemist, not a biologist. So you might have seen, the cat in your house. Whenever you try to intimidate the cat, you might have seen the nail come out from the cat, from the cat's hand. The nail is always there, but it comes out only when it is intimidated, or only when the cat wants to attack. Only then the nail used to come out. So you can clearly see that this kind of action is controlled by what is called the nervous system. Whenever there is a trigger, then only that nail used to come out. The same thing happens in the life of electric eel also. Battery is always there, but to be triggered or not, it will be controlled by the nervous system of that electric eel. Whenever it is intimidated, whenever there is a threat, whenever the species is hungry, that time only this battery will be activated, and it is controlled by the nervous system of the electric eel. I hope this answers your question. And how does it control all those things? The fundamental mechanism, only electric eel knows it. As of now, I do not know. Okay, I think with this, I will go into my today's lecture on electrochemistry, on the fundamentals of electrochemistry. I'll sharing my screen. I hope you will be able to see it now. Are you able to see my presentation? Can anybody answer?
Yes.
Yes, thank you very much. Yes, so let us go into the fundamentals of electrochemistry. And in yesterday's lecture, we spoke a lot about the power of electrochemistry. Electrochemistry, or the science of electricity, has got far-reaching consequences in the life of many species. And the list is so exhaustive that we cannot think anything without electricity. It is that much pervading to our daily life. Not only to our daily life, if you look around also, there are many species, they thrive and survive in this ecosystem by just by utilizing the principles of the science of electricity. And therefore, I concluded yesterday's talk by saying that electrochemistry is very, very powerful. And if you want to use the power of electrochemistry, you must be aware of the fundamentals of electrochemistry. Then only you will be able to manipulate that subject according to your need. You must be aware of the fundamentals of that particular subject. Then only you will be able to manipulate that subject according to your need. So the intention of today's lecture is to take you very briefly through the fundamentals of electrochemistry. As you see here in this particular slide, electrochemistry begins the moment you put an electrode into an electrolyte, into a solution containing ions. And the electrode phase contains a lot of electrons, you can see here. And the solution or the electrolyte contains a lot of ions, you can see here. Remember one thing, electrochemistry happens only at the electrode-electrolyte interface, not in the bulk. See, wherever the electrode meets the electrolyte, electrochemistry will happen there, not in the bulk, not far away from the electrode surface. For that reason, electrochemistry is an interfacial phenomenon. It is an interfacial phenomenon. It happens only at their point of contact. So what is the peculiar aspect of this interfacial region? Interfacial region means their point of contact. The point of contact between the electrode and the electrolyte. What is the speciality? The speciality is, look at this particular diagram that is right in front of us. That is right on the slide. One phase contains electrons, the other phase contains ions, and these electrons can cross the interface as shown by this arrow. If the electron cross the interface as shown by the arrow, what will happen? This phase will acquire a positive charge and the solution phase will acquire a negative charge. And you can clearly see that once the electron crosses the interfacial region, one phase is getting positive, the other phase is becoming negative. There is a charge separation. There is a charge separation, or there is a potential difference building up at the interface. Whenever there is a charge separation, automatically there has to be a potential difference setting up at the interfacial region, and that is the fundamental act in electrochemistry. This development of an electrode potential is the fundamental act in electrochemistry when you dip an electrode into the solution containing ions. And if you look into this particular diagram very clearly, there are two types of electrochemistry now. Okay, there are two types of electrochemistry now. One electrochemistry is talking about the ions in the solution, that is called ionics. That is one aspect of electrochemistry. And second aspect is talking about this electron transfer from this side to this side, and that is called the electronics. There are two types of electrochemistry. One is talking about the ions in the solution, how the ions move under an electric field, how they are hydrated, what is the see what happens when they move towards an electrode surface, all those things. That is called, and what about the ion-ion interaction, ion-solvent interaction, all those things. That electrochemistry part is called ionics. And there is a second electrochemistry part that is concerned mainly about this electron transfer between the electrode and the electrolyte, and that is called the electrodics part of electrochemistry. And this electrodics part of electrochemistry is primarily concerned about the kinetics of that electrochemical reaction, which is extremely important for various reasons. And my question to you is, why this interfacial region? Why electrochemistry is an interfacial phenomenon? Why the interface is very important? Why their point of contact is very important? What is fundamentally happening at the electrode-electrolyte interface? That's the question. Okay, to understand that point, I just draw a beautiful diagram. To me, it is beautiful, may not be for you, okay? It's a very beautiful electrochemical cell, very large electrochemical cell, and I put an electrode into this solution. This is an electrode I'm drawing. Okay. And it is dipped into solution containing ions. And suppose imagine an ion which is far away from the electrode surface. It's a positive ion, just imagine. And imagine an ion far away from the electrode surface. Just imagine, okay, on a time average scale, what will happen is that this ion will see a spatially symmetrical world. Everywhere it will be same for the ion on a time average scale. It is far away from the electrode surface. On a time average scale, this ion will see a spatially symmetrical world surrounding it. Everywhere it is same. It is like you are going to Devagiri College every day. Same teachers, same friends, same canteen, same security, same girlfriend, same boyfriend. No change. So you will not be you will not be excited. You will be in a relaxed state. Everywhere it is same. The ion will feel the same thing. Everywhere it is same. So the ion will be in a relaxed state. Okay, now imagine an ion near the electrode surface. Somewhere here. Now, on the right hand side, it sees the vast electrolyte. On the left hand side, it will see a giant electrode. On the right side solution, left side, a giant electrode. So what will happen? The spatial symmetry experienced by the ion far away from the electrode surface is broken down near the electrode surface. It is broken down. It is no more valid. So what is the consequence? Consequence is ions will be terrified. Ions will be terrified. They'll be anxious. Everywhere it is looking different. Right side solution, left side a giant monstrous electrode. Ions will be terrified. It is like, one day, instead of going to Devagiri College, you went to IISER Trivandrum. Like your, teacher, Dr. Jomon. You know that, One day you decided to go to IISER Trivandrum instead of going to Devagiri College. So you are going for the first time to IISER Trivandrum. The security will ask, who are you? Why you are coming this side? So it is a first-hand experience for you. So you will be anxious. You will be excited. And on top of that, IISER Trivandrum is on the top of a hill. So by looking at all those things, if you are visiting there for the first time, you will be really anxious. The same feeling will be experienced by the ion also near the electrode surface. The ions will be terrified or they will be anxious when they are near the electrode surface because the surroundings looks quite different. What is the consequence of anxiety? Anxiety leads to the building up of tremendous amount of energy. You should know that. For example, a dog chases you. Suppose you are going to meet your girlfriend, for example, sometimes in the evening time to her home or something. And if there is a dog, and if that dog chases you, what will happen? You will have tremendous capability to run faster, much, much faster. Why? Because of the anxiety within yourself. So anxiety leads to the development of or the building of extreme energy within that system. Whenever you are anxious, you are able to run much, much faster. So anxiety leads to the development of extreme energy within that system. So the ion near the electrode surface experience that anxiety. That anxiety leads to what is called the development of extreme energy at the electrode-electrolyte interface. That extreme energy is often called as the electrode potential. And this electrode potential is responsible for the operation of your battery. This anxiety of the ions of the interfacial region is responsible for the operation of the battery, operation of the fuel cell, or whatever you see as electrochemistry. This tension, this anxiety is responsible for whatever you see as electrochemistry. Please keep that in mind. So your interfacial region is quite different from the bulk of the electrolyte for that reason. That is why in electrochemistry, interfacial region is important. Let us look at the development of electrode potential much more in detail. It's important. Much more fundamentally, much more scientifically, because whatever I explained was a philosophical explanation of electrode potential. What is actually happening scientifically when you dip an electrode into a solution containing ions? To understand that, whenever you see, you might have heard about Fermi level. Whenever you take a metallic electrode, whenever you talk about a metallic electrode, it has got a Fermi level. Fermi level is defined as Fermi level. Fermi level is defined as the top of the filled energy bands. It is the top of the filled energy bands. For a metallic electrode, top of the filled energy bands. Just imagine that you are bringing two metals into contact, M1 and M2. The Fermi level of M1 is here, and M2 Fermi level is, for example, is here. Okay, M1 and M2. Suppose you are bringing them in contact. What will happen is that when you bring them in contact, one has a lower Fermi level compared to the other one. The other one has got a higher Fermi level. Okay, what will happen very clearly when you bring them in contact, electrons will flow from this side to this side. If that happens, what will happen? This side will acquire a positive charge and this side will acquire a negative charge. And you can see this process of electron transfer between the two Fermi levels is called Fermi level equilibration. Fermi level equilibration. And you can see what is the consequence of Fermi level equilibration. There is a charge separation building up at their point of contact. If there is a charge separation at their point of contact, automatically there has to be a potential difference building up at their point of contact. And this potential difference is called the contact potential difference. A similar situation happens when you dip an electrode into the solution containing ions. As you know that electrode has got its own Fermi level. Solution contains ions, you know. Ions also has its own Fermi level. I don't want to go into all these things. I'll skip all these things. Okay, just give me a moment. Yes. So the electrode has got its own Fermi level and the solution has got, you know, it has got highly occupied MO, highest occupied MO, lowest unoccupied MO, all those things, you know it. And the Fermi level of solution is defined as the level where the probability of occupation is 50%. That definition is not important. What is important is solution also has, the solution species also has got its own Fermi level. Metal has got its own Fermi level. Solution species also has got its own Fermi level. Now imagine a situation like this. When you dip an electrode into the solution containing ions, just imagine that the Fermi level of the metal is higher than the solution species. This is metal, this is solution species, okay? And you can see the Fermi level is higher, the Fermi level of metal is higher than the solution species. And if you dip that electrode into the solution containing ions, automatically during the Fermi level equilibration, electrons will be transferred from the metallic electrode into the solution species during the Fermi level equilibration. If that happens, what will happen? The metal side will acquire a positive charge, solution side will acquire a negative charge. The opposite side is equally possible. The opposite situation is equally possible. This is metal. The Fermi level of the metal is lower than that of the solution. In that case, electron transfer will be in the opposite direction. It will flow from the solution species to the electrode surface. What will happen in that situation? What will happen is that the metal side will acquire a negative charge and solution side will acquire a positive charge. In any case, during the Fermi level equilibration, you can clearly see that there's a charge separation at the interfacial region at their point of contact. If there is a charge separation, there has to be the development of a potential difference at their point of contact. And that potential difference is called the electrode potential. That potential difference is called the electrode potential, and that potential difference is given by the famous Nernst equation. That potential difference is given by the very famous Nernst equation. And for example, if you dip a platinum wire into a solution containing Fe2 plus and Fe3 plus, as shown in this picture, in this slide, to write the Nernst equation, first you should write the electrochemical equilibrium responsible for that. Remember that to write the Nernst equation, you know the origin of electrode potential now. It is the Fermi level equilibration, there is charge separation, and that is leading to the development of an electrode potential. Okay, and now to write the Nernst equation, you should know what is that particular electrochemical equilibrium. Look at the platinum wire. What is there on the platinum wire? On the platinum wire, we have a lot of electrons. Okay. What about the, so one thing I should, tell you here before writing the electrochemical equilibrium, we always write the reduction reaction. The electrochemical equilibria will be always a reduction reaction, mainly because we follow IUPAC convention. If you go to the US, you will be finding that they will be following an oxidation reaction. They follow a different convention. It doesn't matter, but we follow the reduction reaction. That is the reason why all the electrode potentials are standard reduction potentials. Keep that in mind. All the electrode potentials are reduction potentials in India and many of the European countries because we follow IUPAC convention. So the electrochemical equilibria has to be a reduction reaction for that reason because we follow IUPAC convention. Okay, so we have to write the reduction reaction for this particular system. On the electrode surface, you have platinum. On the electrode surface, you have electron. And what is the oxidized species now? Oxidized species is iron 3 plus, iron 3 plus. What is the reduced species? Iron 2 plus. Just write that, it is done. That is on the right hand side. The oxidized species on the left hand side, reduced species on the right hand side. Your electrochemical equilibrium is ready now. And I said, whenever you dip an electrode, there will be an electrode potential, and that electrode potential is given by the famous Nernst equation E is equal to E0 plus RT by NF Ln concentration of Fe3 plus divided by concentration of Fe2 plus. The concentration of oxidized species divided by the reduced species. It is not actually concentration, it is activity. But for time being, we assume that activity is equal to concentration. Activity means effective concentration. For example, when you dissolve some electrolyte into a solution, to form a solution, for example, you dissolve 1 molar of the electrolyte, the effective concentration can be lower than most of the time 1 molar concentration. Because of ion interaction, ion solvent interaction, ion pair formation, because of all these complexities and complications, it is possible that the effective concentration is lower than 1 molar concentration. And that effective concentration is called activity. And that is a term you should use in the Nernst equation. But for time being, let us assume that activity is equal to concentration. So this is the Nernst equation which we have right now. E is equal to E0 plus RT by NF Ln concentration of Fe3 plus divided by Fe2 plus. Where R is the gas constant, T is the temperature, N is the number of electrons, F is the Faraday constant, E0 is called standard reduction potential. Standard reduction potential. It is a reduction potential at 25 degrees centigrade at pressure is equal to 1 atmosphere. And when the concentration of all the species, Fe3 plus concentration of Fe3 plus, Fe2 plus. It's not the concentration activity, okay, but for time being, let us assume it is concentration. When concentration of Fe3 plus, Fe2 plus all are equal to 1. So under that condition, the electrode potential will be E0, that is called standard reduction potentials. I'm sure you all know that. Now, the interesting thing here is this equation, which is right in front of you. The origin of this equation is when you dip an electrode into the solution containing ions, okay? So this electrode potential is active only at the interfacial region. I repeat it because that is very important. Most of the people forget that. It is active only at the interfacial region. And the dimension of the interfacial region is not very large. It is in the order of 1 to 10 nanometer. This is very important. The dimension of the interfacial region is 1 to 10 nanometer. And the electrode potential can be, a few volts, maybe 1 volt. If you take it as 1 volt, most of the time, it can be 1 volt, it can be 2 volt, it can be 3 volt also. But most of the time, it will be a few volts. Remember one thing, this 1 volt is acting in a very narrow interfacial region, as shown here. You can see here. It is acting in a very narrow interfacial region. For that reason, the gradient of electric field or electric field strength is equal to the voltage divided by the distance in which it is acting. The voltage, I said, it can be, if you take it as 1 volt, it is 1 volt divided by the distance in which it is acting. Distance is 10 nanometer. If you take it as 10 nanometer, what will be the value now? It will be 10 to the power 8 volt per meter. You can see that. The electric field strength is 10 to the power 8 volt per meter. It's a huge field strength existing at the electrode-electrolyte interface. And that is why your battery is so powerful. That is why your fuel cell is so powerful. That is actually what is the essence of electrochemistry. This huge electric field strength existing at the electrode-electrolyte interface of the order of 10 to the power 8 volt per meter is actually the essence of electrochemistry. It is the power of your battery. It is the power of your solar cell. It is the power of your fuel cell. It is the power of electrochemistry. It is the essence of electrochemistry. And if you go back to the next equation, I will rewrite one more time here. For the system we discussed, the platinum electrode in solution containing Fe2 plus and Fe3 plus, I'll rewrite the next equation one more time here. E is equal to E0 plus RT by NF into ln natural logarithm, concentration of Fe3 plus by concentration of Fe2 plus. It is 2 plus 3 plus divided by 2 plus. I hope you can see it. My handwriting is very bad. Okay, now this equation says there are 2 types of electrochemistry possible. There are 2 types of electrochemistry that is possible at the moment now. The first type of electrochemistry is you adjust this concentration ratio. For example, if you increase this concentration ratio, automatically this electrode potential will increase. If you decrease this concentration ratio, electrode potential will automatically decrease because they both are connected. So according to the concentration ratio, the electrode potential will be adjusted, and that is called equilibrium electrochemistry or potentiometry. And it has got a lot of applications. For example, your glucose sensor is based on this kind of principle. For example, I'll show you very briefly what is that. You have the electrode potential. If you plot the electrode potential on the y-axis and log of this concentration ratio, Fe3 plus by Fe2 plus, on the x-axis, you will end up with ln Fe3 plus divided by Fe2 plus. If you plot this on the x-axis, electrode potential on the y-axis, and you take non-concentration ratios of Fe3 plus and Fe2 plus, you increase the concentration ratio. What will happen? The electrode potential will increase like this. Linearly, it will increase. And you take your unknown concentration ratio, just measure the electrode potential, and then just extrapolate it. Measure the electrode potential, extrapolate it, you will get the unknown concentration ratio. So this is the power of this technique called, this electrochemistry called equilibrium electrochemistry or potentiometry. That's very, very important. And the second electrochemistry is, there are two types of electrochemistry possible. One we discussed. Second electrochemistry is, you adjust the electrode potential, and automatically, for example, when you increase the electrode potential, automatically this ratio will increase. If you decrease the electrode potential, this ratio will decrease automatically. Concentration ratio on the right-hand side. And that is called dynamic electrochemistry. So the next equation says that there are two types of electrochemistry possible. One is equilibrium electrochemistry. Second one is dynamic electrochemistry. I hope that that aspect is very clear. And the most important thing I wanted to emphasize here is not about all these things, but the electrochemical thermodynamics. The derivation of Nernst equation is given here. I don't want to go into those details and all. What I want to emphasize here is about the thermodynamics of electrochemistry, electrochemical thermodynamics, because it is extremely useful, electrochemical thermodynamics. See, you know this particular relation, relating delta G with electrode potential. Delta G is equal to minus N of E, where N is the number of electrons, F is the Faraday constant, E is the electrode potential. So, by measuring the electrode potential, it is possible to measure the free energy of a reaction. That is the power of electrochemistry. Just by measuring the electrode potential, it is possible to estimate the free energy change for that particular electrochemical reaction. And you know this particular relation from thermodynamics, dG is equal to VdP minus SdT. That says that if you take del G by del T P, what will happen is that this equation will become equal to minus S, which means del of delta G by del Tp will be equal to minus delta S. It's a simple mathematical manipulation, but delta G is equal to minus N of E. So if you put those into this equation, you will get NF into del E by del Tp is equal to delta S. It's a very, very important relation in electrochemistry. Or I can write like this, del E by del Tp is equal to delta S by NF. Simply again mathematically rearranging it. What is this del E by del Tp? It's the ratio of electrode potential and temperature. It is called the temperature coefficient of electromotive force. And that is equal to the entropy change of that reaction. So if you know the variation of electrode potential with respect to temperature, you can actually measure the entropy change for that reaction. And del E by del Tp is called temperature coefficient of electromotive force. it has got a lot of consequences, this particular relation. For example, if you take a hypothetical reaction, A plus electron going to B, just imagine, okay, a reaction like this. And just assume that delta S for this reaction is positive. If delta S for this reaction is positive, what about this relation? This relation says that the temperature coefficient also should be positive because both are equal. Which means if I plot a graph between electrode potential and temperature, the slope of the graph will be positive, like this, for that reaction. Why? Because the slope of the graph is nothing but del E by del Tp. And that is positive because entropy change is positive here, you can see. For that reason, if you plot electrode potential versus temperature, the slope of the graph will be positive. Because slope of the graph, or del E by del Tp, is nothing but the entropy change, and the entropy change happened to be positive here. So the slope is positive. And this plot is extremely important because it says something very exciting to you. Look at the x-axis. Look at the x-axis of the plot. You increase the temperature. And then look at the y-axis. Your electrode potential is concomitantly increasing. When you raise the temperature is the one you provide to the electrochemical cell. And electrode potential is from the electrochemical cell. So you provide temperature to the electrochemical cell, and then you measure the electrode potential. And you see, when you raise the temperature, electrode potential is concomitantly increasing. What does it tell you? It tells you that you can also look at it. When you increase the temperature, electrode potential is increasing. When you decrease the temperature, electrode potential is decreasing. See that? This says that simply if the entropy change of the reaction happens to be positive, you can also interconvert the temperature gradient also into electrical driving force. You see, when you raise the temperature, electrode potential is increasing. When you lower it, electrode potential is decreasing. It says that when the entropy change of the system happens to be positive, you can also interconvert the temperature gradient also into electrode potential or electrical driving force or electromotive force. So you can interconvert the temperature gradient also into electromotive force if the entropy change of the reaction happens to be positive. And this is the principle of what is called thermogalvanic cells. Thermogalvanic cells, where they interconvert the waste heat into electromotive force by choosing a reaction which has got a positive entropy change. And this plot is simply the principle behind thermogalvanic cells, or the interconversion of waste heat into electromotive force. That is called thermogalvanic cells. On the other hand, if the entropy change of the reaction happens to be negative, delta S is negative, then automatically del E by del Tp will be negative. Then what will happen? Your electrode potential will decrease when you increase the temperature, like this. So here delta S is positive. In this case, delta S is positive. And in this case, delta S is negative. So the temperature coefficient of EMF is an extremely important parameter in electrochemistry. And by looking at that parameter, you will be able to understand the entropy change of the reaction and vice versa. So the electrochemical thermodynamics is extremely, extremely important. And also by looking at the electrode potential, it is also possible to predict the spontaneity of a reaction. You know that when delta G is equal to, when delta G is negative, that reaction will be spontaneous from thermodynamics. When the reaction has got a negative free energy change, you know that the reaction will be spontaneous. For example, you look at this particular reaction, and that spontaneity judgment can be simply made by looking at the electrode potential. For example, you look at this particular reaction. This particular reaction has got, when you go from left hand side to the right hand side, when you go from left hand side to the right hand side, you see your electrode potential is plus 1.83 volt, which means delta G will be equal to minus NF into plus 1.83 volt. From left hand side to the right hand side, when you go from left hand side to the right hand side, the cell voltage is positive. Cell voltage is positive means free energy change has to be negative, which means the reaction from left hand side to right hand side is spontaneous. What about the reaction from right hand side to left hand side in this direction? The cell voltage for this reaction has to be negative. If it has to be negative, delta G will be positive, which means the reaction will not be spontaneous. What is that reaction? The reaction of gold with acid to form hydrogen. Is the reaction from right hand side to left hand side. And that reaction is non-spontaneous, means gold will not react with H plus to form hydrogen under standard conditions. So you can predict the feasibility, the spontaneity of a reaction by looking at the electrode potential. I have one more example here, that is this reaction. These are all very important, you know, for many competitive examination, this kind of questions may come. So you can pay some attention to it. For this reaction of lithium in acidic solution, lithium metal with H plus, the electrode potential is minus 3.04, which means when you go from left hand side to the right hand side, the electrode potential is negative, which means delta G will be positive, which means the reaction from left hand side to right hand side is non-spontaneous. What about the reaction in the reverse direction? Right hand side to left hand side, it will have a positive electromotive force plus 3.04 volt, which means delta G will be negative, which means the reaction from right hand side to left hand side will be spontaneous. What is that reaction? The reaction of lithium solid with H plus to form hydrogen. That reaction is spontaneous, and that is why lithium metal violently reacts with H plus to form hydrogen. That is why people say lithium can replace H plus from acidic solutions. So what I'm trying to tell here is that by looking at the electrode potential, it is possible to predict the feasibility or spontaneity of an electrochemical reaction. Okay, now I'm going to the most important part of my discussion. Okay, this is very, very important. The power of electrochemistry is at the electrode-electrolyte interface. It is residing simply at the electrode-electrolyte interface, not anywhere in the bulk. So we must understand that interfacial region much more in detail. Then only we will be able to manipulate it. If you want to use that interface for your benefit, you must have much more understanding about that interfacial region. Okay, to do that, let us start with again our discussion. I am dipping an electrode into the solution containing ions. One phase contains electrons, other phase contains ions. This is the solution phase, this is the metal phase. I'm dipping that electrode into the solution. I imagine that my metal is actually a tank full of electrons. It is just my imagination, okay? My metal is a tank full of electrons. Full of electrons. And solution is another tank full of ions. positive ions, negative ions, positive ions, negative ions, plus, minus, like that. So this is my solution. So there are two tanks. I am dipping the electrode into the solution means it is analogous to connecting the two by a tube. I am dipping the electrode into the solution means I am connecting the two by a tube. And both are in contact now. One tank, metal tank, solution tank, and both are connected by a tube. That is the meaning of dipping the electrode into the solution. And along this tube, electrons can actually move like this. If the electrons move like this, what will happen? The left-hand side tank will acquire a positive charge, and the right-hand side tank will acquire a net negative charge, which means the left-hand side tank will be positive, right-hand side tank will be negative, like this. What is this electronically? Electronically speaking, what is this charge separation? Can I ask from the audience if they are not sleeping? Electronically speaking, what is this? What is this charge separation? I am waiting for your response.
You can type in the response in the chat box.
Anybody? Electronically speaking, in terms of real world electronic components, what is this? It is a potential difference, I agree. What is that component? There is a charge separation, plus and minus. One plate is positive, other plate is negative. What is that component's name? Is it a resistor, capacitor,
Battery.
inductor? Yes, it's a capacitor. Somebody wrote in the chat box. It's a kind of capacitor now, because you can see one plate is positive, other plate is negative. Okay, that happens when you dip a metal into the solution. But the most important thing is, one more thing we have missed out here. We forgot the tube. Tube is still there. One plate has become positive, agree. Another plate became negative, I agree, but the tube is still there. What is the purpose of the tube? Electron transfer, electron flow. What is this tube in terms of real world electronic components? Can anybody say? Can anyone say? Quickly. What does this tube stand for in terms of real world electronic components? Yes, go ahead. If you take time to answer the question, I will take time to complete the session. I know you all want to complete it as early as possible. So if you want that, please answer the question as early as possible. Not interface. I'm talking in terms of real world electronic components. What is that component? The tube. One component is capacitor. What about the other component? The purpose of the tube is electron flow. So what is that? Electron flow. In electronics, electron flow happens across what? Wire. So what is that wire?
Conductor.
Yes, it's a conductor, or in more sophisticated way, it's a kind of a resistor. You got it right? Conductor means resistor only. Okay, so it is simply a resistor like this. That is the tube is standing for. Now you see, this is actually the electronic model of your. This is actually what is at the electrode electrolyte interface. What is this? It looks very strange. It is not strange. If I rearrange it, you will understand it. It is simply one plate is positive. This is what the situation we had. In the middle, you had a resistor. The same thing I'll write like this. One plate is like this, and on top, I'll write the resistor like this. So this plate is plus, this plate is minus. The same thing. The same thing. The same thing what you have here is the same thing only in the top. So this is actually the electronic model of your electrode electrolyte interface. the electronic model of your electrode-electrolyte interface is a capacitor in parallel to a resistor. It's very, very important. A capacitor in parallel to a resistor, that is the simplest electronic model of the electrode-electrolyte interface. When you dip an electrode into the solution, this is what is actually the appearance of your electrode-electrolyte interface. A capacitor in parallel to a resistor. So what is the consequence of that? Okay, you agree that your interfacial region looks like this, a resistor in parallel to a capacitor. Okay, this is the structure of your interfacial region. Now, suppose I apply a voltage difference across this circuit. Okay, the voltage of this circuit will change only when the charges build up on this plate, plus on this side, minus on this side. If the charges cannot build up, the voltage will not develop across the capacitor plates. Very important. If more charges build up, more potential difference. Less charge build up, less potential difference. I think it's very clear. If the charges cannot build up, there won't be any potential difference across the plate of the capacitor. Now imagine a situation. This resistance tends to infinity, very high value. Imagine a situation like that. Resistance is very high. And I am plotting a graph between current and potential. Current and potential. Please be with me for some more time. I'm going to wind up very soon. Don't sleep. It's very important. If you stay with me, I'll finish it faster, okay? The case number one is your resistance value is very, very high, infinity. And I am changing this potential now. And I'm plotting a graph between current and potential. Current will flow only if the charge moves across the resistor. Otherwise, there won't be any current flow. Keep that in mind. Okay. Now I'm changing the potential. Since the resistance value is very, very high, there won't be any charge passing through the resistor, which means the current will be close to zero. Current will be close to this range. What about the potential? When you change the potential, charges will accumulate on the plate, simply like this. Why? Why? Because the charges cannot move through the resistor, because the R value is very, very high. So they will accumulate on the plate. If the charges accumulate on the plate, the potential will change, just like that. But since the R value is very high, there won't be any current flow, which means that under this situation, the potential will simply change without a current flow. The potential will simply change without a current flow. And this interface is called polarizable interface. I am coming to a very, very important point. Imagine the opposite situation. Opposite situation is simply you have the resistor and you have a capacitor, and you do the same thing. You apply a voltage. Okay. So, but the situation is R tends to 0. Resistance value is very, very small. And you are changing the voltage. What will happen now? What will happen? Very simply, because since the R value is very small, charges will move through the resistor, which means you can expect a current flow. Since the R value is very small, charges cannot accumulate. It cannot accumulate on the plate. If the charges cannot accumulate on the plate, what will happen? The voltage won't change, but the current will change. So you will have a situation like this. There is a current flow without a voltage change. And this interface is called non-polarizable interface. This is very, very important concept. Okay, it is not very difficult to understand. If you pay some attention, it is very, very easy. Non-polarizable interface. Now tell me, look at these two plots. You have two types of interfaces. One is polarizable, one is non-polarizable. Which one can function as a reference electrode? The purpose of reference electrode is to provide a constant potential so that we can measure the potential of any other electrode accurately. Now, from these two plots, what should be the behavior of a reference electrode? I am asking the student audience before they leave all. What should be the, okay, non-polarizable. Asha S. Matthew wrote that it is non-polarizable. Excellent. Because in the case of non-polarizable interface, you can clearly see that the voltage is constant even though there is a current flow. So the behavior of reference electrode should be like this. Any reference electrode should be non-polarizable. Then only it can give a constant potential. Then only you can measure the potential of any other electrode with respect to that electrode. That is the reason why your standard hydrogen electrode, is a reference electrode. Why standard hydrogen electrode is a reference electrode? Because of this particular behavior. There won't be any voltage change even though there is a current flow. That is why standard hydrogen electrode is a non-polarizable interface. That is why it is used as a reference electrode in electrochemistry. I'm coming to the last part of my discussion. So how do you use standard hydrogen electrode to measure the electrode potential of other electrodes? It is very simple. First, you construct your standard hydrogen electrode. It is very simple. You take an electrochemical cell and you take some HCl solution of unit activity equal to 1. And then dip a platinized platinum electrode, bubble hydrogen gas at 1 atmospheric pressure. And then, so your standard hydrogen electrode is ready now. Then you bring your other electrode, whichever be the electrode. For example, if you want to measure the potential of copper 2 plus copper, take the copper 2 plus solution, take a copper electrode, connect the 2 electrode by a voltmeter. Okay. It is insufficient. You also have to connect the 2 solutions by a salt bridge. Then only there will be a communication between the electrolyte. Once you do that, you have 2 types. This is your copper 2 plus electrode. So this is your right hand side electrode. This is your left hand side electrode. Okay. And according to IUPAC convention, the E cell now, the total cell voltage that you measured in the voltmeter here is equal to ERHS right hand side minus ELHS. And ELHS is always taken as 0 by convention. So it will be ERHS minus 0, which means ERHS. So whatever the voltage you measure in the voltmeter is equal to the right hand side cell voltage. What you do simply now, you change this electrode now to maybe to zinc 2 plus, measure the voltage difference. You change it to platinum 2 plus, lithium plus, sodium plus, like that. Simply measure the electrode potential with respect to standard hydrogen electrode. That is how your electrochemical series is constructed. It's simply by measuring the voltage difference between SHE, standard hydrogen electrode, and that electrode. Just by using a voltmeter, you can measure the electrode potential of various other electrodes. And that is how the electrochemical series is constructed. And the last part of my discussion is, you will see that in the electrochemical series, some electrode potentials are negative. For example, lithium bar lithium plus, it is minus 3.04 volt. It is minus. Whereas some, like O2 bar water, is plus 1.23 volt. What I'm trying to tell here is that some electrode potentials are negative, some are positive. What is the meaning of negative and positive? It's very, very important. If you know the meaning of this negative and positive, anybody can make a battery, anybody can make a fuel cell. If you know the meaning of this. Negative means simply it has more number of electrons. In a layman's language, positive means it is deficient of electrons. Keep that in mind, okay? On a standard hydrogen scale, negative means it has more electrons. Positive means it is deficient of electrons. If you understand this concept, you can make a battery. I'll show you. How do you make a battery? There's the last part. The construction of a battery, any battery, anybody can make a battery. Construction of a battery is like constructing a 2-bedroom flat. Two-bedroom flat, very simple. What you should do? You should construct the first room or the left-hand side room by taking a negative electrode from the electrochemical series. For example, zinc 2+. The electrode potential of this electrode is from the electrochemical series is minus 0.76. It is minus. Construct the left-hand side room by taking the negative electrode from the electrochemical series. Construct the right-hand side room, second room, by taking a positive electrode from the electrochemical series. For example, copper 2+. The electrode potential of this electrode is plus 0.34. So one is negative, one is positive. Left-hand side room is ready, right-hand side room is ready. Now what you should do? 2-bedroom flat now, you should have a roof. Construct the roof by connecting the two by a wire. Your roof is ready. Construct the roof by connecting the two electrodes by an external wire. Now the roof is ready, rooms are ready, but I would say battery is not ready because the two rooms are not connected now. For example, you are in this room, for example, you are in this room and you want to move to this room from here to here. How do you go? It's a 2-bedroom flat now. You cannot jump through the roof. People will think that you are a thief. You have to walk and go. How do you do that? So the best way, what you do is that you actually connect the two rooms by a salt bridge. Simply. So if you make a connection between the two rooms by a salt bridge, you will be able to go from this side to this side without jumping through the roof. Your battery is ready now. Negative and positive. This side is negative, this side is positive. Negative means more electrons, positive means deficient of electrons, which means electrons from this side will have a tendency to move to the right-hand side. And in that process, you will get electricity. So when you do this kind of configuration, by coupling a negative electron with a positive electrode, electrons will have an automatic tendency to move from left-hand side to the right-hand side. In that process, you will get electricity. And that is the principle of any battery or any fuel cell. Anybody can construct a battery if you understand this concept properly. I wind up my talk here. Thank you very much. If you have any questions, I'll be happy to take it.
Yes, students, this is open for discussion. I mean, if you have any question, you can ask.
Asha.
You can type also the question. I can read it if you are afraid of me. Yes.
Mustafa sir, there is a small query. Is
Yes,
there only
please.
electrochemistry limits us ourselves with just the 2-bedroom one, or is there a 3-bedroom possibility?
Okay, may I know who asked this question?
Tanya.
Okay, okay, fine. See, for electrochemical devices, it is always only a 2-bedroom option. 3-bedroom flats are not possible in electrochemistry. But if you really want to investigate the fundamental electrochemistry, of course, we have to worry about 3-bedroom flat, where we do what is called cyclic voltammetry in a 3-electrode configuration, where of course you have
Scope for
3.
more.
Yes. But I tell you that there is no scope for 4-bedroom because electrochemists are very poor. I'm sorry.
I know.
Okay.
This is just a joke. Okay,
Sure.
Thank you.
No
Thank
problem.
you.
Yeah. Yes, I see that Asha S. Matthew, somebody asked a lot of questions. No? So I think you can ask one question. Because it is better to address them with the name so that you know.
I think everyone is very clear with the concept because you have explained in such a simple manner.
True.
I don't know. I'm unable to believe it anyway. Fine. Okay.
Probably they'll put it up in the Google form, if at all.
Okay, sure. So tomorrow, anyway, a happy news for all of you. Tomorrow will be the last lecture. Okay.
So, we look forward to the fuel cell section.
Okay. Okay. So tomorrow will be the last lecture, but I'll make sure that tomorrow the concept is. If you miss the lecture tomorrow, I think you miss the beauty of electrochemistry.
Yes.
Okay, Asha S. Matthew, I'm a biochemistry teacher, so excited to learn electrochemistry. Thank you. Okay, great. Okay, so we'll see tomorrow. Tomorrow we'll be discussing about double layer theories, and that is the most difficult part of electrochemistry. And if you miss that, you miss everything in electrochemistry. You may not miss Mustafa, but you will miss the beauty of electrochemistry. But Tanya, definitely I enjoyed the question. Okay, thank you.
Thank you. This is really a relearning, as Asha Miss was pointing out. Electrochemistry relearned in a different way.
Okay.
And it's really helpful for the PG students of University of Calicut in that they are actually going to learn in 3rd sem the electrochemistry concepts.
Okay.
So thank you on behalf of them as well.
No problem. Thank you very much for inviting me. Okay,
And
so
that-
yes.
That too, 1 hour of electrochemistry lecture without mentioning anode and cathode. That's what I was noting.
No, I was waiting for you, Dr. Manoj, but I could not see you. Anyway, so
Okay, thank you so much.
yeah, thank you very much. So see you tomorrow then. Same time, right, Jomon, right?
Same time.
Yeah, thank you, Dr. Manoj, Dr. Jomon, Dr. Tanya. Bye.
Yeah, thank you, Dr. Mustafa, for such a wonderful session today also.
I
And
don't
thank
know
you all.
how wonderful it was, but it's. Okay, I think I could do some justice, I believe.
Yeah, and personally for me, I have never listened an electrochemistry in such a simple manner. I mean, that's my personal experience.